about limits, and it's about a more formal way of finding limits, rather than in the previous section, which is more about just kind of visually looking at it. This kind of walks us through the formal ideas of it. Sure. Okay. So you'll be very excited about that. So there's a bunch of limits that we're supposed to be able to do. All right. So in the book, there's this big box on page 77. It talks about limit laws. We will almost never use those limit laws. They're very specific kinds of things, but they're really, really simple, pretty straightforward kind of. But glance at them. Mainly because I want you to become comfortable with the notation that they use. So when you see the notation, you don't freak out. There's a ton of notation dealing with limits, and you have to be able to read it and understand it and feel comfortable with it. Because one of the main emphases that we use in PAL is the limit of the difference quotient, which we started last year. But it gets more complicated, and so you have to be comfortable with that concept. So go look at this, make sure that you understand it. Essentially, this is what it says. If you started off with just this little simple problem right here, the limit is x approaches 3 of x plus 2. Find the limit. Well, what the limit laws say on page 77 that you're allowed to do is to take and kind of distribute this sort of to both of these. So it would be the limit of x as x approaches 3, and then it would be the limit of 2 as x approaches 3, and you can separate those into two separate things. Now, does it make sense that as x approaches 3, that x is getting closer and closer to 3? So the limit is, are you getting closer to 3? Not supposed to be hard. It's like, yeah, duh. It's supposed to be, yeah, duh. What's 2 getting closer and closer to as x gets closer and closer to 3? 2. Because what this really is, it's like the equation y equals x. That's that one. But this is like the equation y equals 2. So that's just a horizontal line. All right. And so, as x gets closer and closer to 3, I'm still just 2. So what this becomes, this guy is approaching 3, this guy is approaching 2, and the sum of them is approaching 5. Now, here's why we don't use this. Is what the limit laws want you to do and how they want you to think about it. But what you really can just do is take 3 and plug it in. 3 plus 2 is 5. Without having to rewrite it that way. In the book, they're going to say in some of the homework problems, using the limit laws or something like that. Don't worry about doing that. Just be able to plug it in. Almost always evaluate a limit by just plugging the number in. Now, of course, the ones we're going to give you are the ones where you can't do that. And you have to do some other things. But I'll get to that in a second. All right, so here's this concept. The limit of f of x approaches a is equal to L. L refers to the limit. So in the last problem, 5 was the limit. That's what the equation x plus 2 was approaching as x was approaching 3. As x got closer and closer to 3, that answer got closer and closer to 5. Now, in math, the if and only if concept means it works both ways. So, the limit of f of x as x approaches a of L, if and only if this is true. Alright, so look what this is saying. This is saying that the limit of this function as x approaches a, and that means from the left is equal to the limit of f of x as x approaches a from the right. So when you see this symbol, that notation is referring to a two-sided limit. A two-sided limit. Then what you're coming to from the left and what you're coming to from the right have to be the same thing for the limit to exist. If it's not true, if the limit from the left and the limit from the right aren't the same, then the limit doesn't exist. In this section, when you see notation like this, you see stuff like this right now, don't just kind of do this mind blur, where you just, your eyes just skim over it, you don't read it. Read the vocabulary. The limit of f of x, as x approaches a, from the left, equals the limit, which is equal to the limit of f of x as x approaches a from the right. Read that in your head. Force yourself to slow down and read the vocabulary and the notation of the mathematics. So here's what that says. I've got some function, this is f of x. I've got some function curly q. So what's the limit as, let's write this out, the limit as x approaches 3 of f of x. Well, as I come to 3 from the left, this function value appears to be getting closer and closer to 2. As I come to 3 from the right, I did this just backwards. Let me try that again. As I come to 3 from the right, I'm approaching 2. As I come to 3 from the left, I'm coming to 2 also. So since the limit from the left is equal to the limit from the right, then the limit exists and is equal to 2. We're going to do this a lot this year. We're going to have some stuff like this. It's like, yeah, duh. But what happens a lot in some of the concepts we have is we put very formal definitions to some things. And it's upon those formal definitions that calculus is developed. And so the mathematicians, we're not going to do all the stuff, like we're going to skip section 2.4 here, which is about the formal definition of limit. We're kind of doing this intuitive definition of limit, and that's fine for us. Going to BC Calc or Console Calc will be all about the formal definition of limit. We're going to skip that this year. But we will put a lot of seemingly overkill into some things, that seem kind of obvious, but just kind of have to go with it. All right, so having that little bit of knowledge about limits shows the limit of the absolute value of x is x equals 0, which is 0. Well, absolute value always is a piecewise defined function. Remember what we just said about the limit. For a limit to exist, the limit from the left and the limit from the right have to be equal to each other. So if I want to see what's happening as I approach 0, I have to look at it from the left and look at it from the right. So let me break this up. Oh, by the way, the absolute value of x is a piecewise defined function. The absolute value of x is x as long as the x is greater than or equal to 0. But the absolute value of x is negative x if x is less than 0. So now listen to the limits. The limit from the left has to equal the limit from the right. If I say, show that a limit exists, you need to do that. You need to show the limit from the left is equal to the limit from the right. So, show this limit exists. So, to show that that limit exists, I'm first going to look at it from the right. If I come to 0 from the right, what does that mean about the absolute value of x? It's positive. Which is why suddenly the absolute value sign went away. Because the absolute value of a positive number is just the number. Now let's look at what happens as I approach 0 from the left. The absolute value of absolute value of x from the left, well, if this is a negative thing, then I have to take the opposite of that negative thing. That's the definition of absolute value. But, remember how I said whenever possible, just plug the number in? So now let me take the limit. So I'm allowed to just plug 0 into there. So when I plug 0 in, I get 0. When I plug 0 in over here, I take the 0 and plug it in there, I get 0. Is the limit from the left equal to the limit from the right? Yes. Therefore, my theorem 1, read that in your book, that's what I just cited. The the limit from the left has to equal the limit from the right. The limit of the absolute value of x as x approaches 0 is 0. I will give you problems like that. Right? Provable limit. That's the proof. All that work I just did was the proof, showing the limit from the left is equal to the limit from the right. Or, as the case may be, show that the limit doesn't exist. Second example. Find this limit. Oh, look, you say. It's an absolute value. Therefore, I'm going to need to show both sides of this. So first thing I'm doing is looking at the limit from the left. So when I look from the left, the absolute value, that's going to make this negative. So that means I need to choose the opposite of that number. And so x divided by x cancels, leaves negative 1. So the limit is x approaching 0. Negative 1 is negative 1. Yay! That's from the left. Now, that's from the right. As I come to 0 from the right, that means that this absolute value is just the positive version of that. And x divided by x becomes 1. And as x approaches 0, 1 gets closer and closer to, well, it's already there, 1. So the limit from the left was negative 1. The limit from the right was positive 1. Since the limit from the left does not equal the limit from the right, since those guys aren't equal to each other, the limit does not exist. Girls. You know the movie? I mean, that's like the big aha at the end of the movie. The limit does not exist. My point exactly.
I used to follow that last year every 2 minutes, like every class.
So, since these two things aren't equal to each other, then you say the limit does not exist. You just write DNE if you want. Save 3 seconds of your life. Now, graphically, kind of back to point 2, graphically, this is what this looks like. That's what this graph looks like. When x is positive, you just get x over x, which is 1. So from here over is equal to 1. When x is negative, if you come from the left, you get negative 1 over 1, and so you get negative 1. Notice, by the way, both of these are open circles because the function's undefined at 0.
So if one of those is like a filled-in bubble, would it be 1?
What do you want?
Because like you said, doesn't exist.
The limit doesn't exist.
But if the was filled in.
Well, it can't be filled in because this is in the denominator. So I can't be ever equal to 0, then the function is undefined. So it's not because the function's undefined at 0 that the limit is 0. It's undefined because the limits from the left and the right aren't equal to each other. Squeeze theorem. Practice this later. Go squeeze somebody. That was a little evil sounding. I will not ask you to use this, but it comes up occasionally through the year. The book will cite this theorem, and I want you to kind of understand the premise behind it. The idea is, let's say I know that the limit of this function as x approaches 0 is equal to 0. Right? Look at the graph. Blue curve. As I get closer and closer to 0, the function's value gets closer to 0. And look at the red function. The limit as x approaches 0 of this function, let's call it g of x, it also equals 0, right? So then look at the black function. What's the limit as x approaches 0 of, call it h of x? Well, if I somehow know that this is true, above the red line. But if these two guys approach the same value, and the black one's always in the middle, does it make sense? It also has to approach the same value. If I'm always between these two guys and they're coming in closer to zero, I've got to be getting closer to zero too. That's the phrase squeeze. It's getting squeezed in between these two. And so whatever they are approaching is what you're approaching also. Yep.
Have to be like, would they have to write like from the left or the right? Because like in the parabola, it's like at one point they would like kind of like evolve into like other sides. Like if you like figured that one, the other side wouldn't be the squeeze anymore unless it was approaching from the left.
Well, if it's always between these two, then it does something like that. It's always between. So this statement is saying that H is always squeezed between F and G. So if I'm always between F and G, then whatever. If these guys are approaching the same number, then I've got to be approaching that number too. I'm not going to ask you to use it, but occasionally, like I said, it comes up in the book. Kind of have that in the back of your head. Oh yes, they just get squeezed in the middle. So on this kind of a problem, on this kind of a problem, you'll almost never see this kind. But this is how you find the limit. This is the limit of 2x plus 5. 2x plus 5 as x approaches 3. Whenever possible, just try to plug in the number. Plug in 3. 3 times 2 is 6. 6 plus 5 is 11. That's the limit. And of course, you'll almost never get this kind of problems. But when possible, plug it in. So let's try to plug in 0. And what do you notice? Your house blows up. I hate it when that happens. Right? Okay, it's undefined at that point, right? Because of the 0 in the denominator. So, I don't know if you remember this or not, but last year I said to you, I would never require you to rationalize the denominator again, right? When we had fractions like 2 over square root 3, I was fine with that. But I said there was a reason to be able to do the rationalization concept, and this is where it comes in, on problems like this. Instead of rationalizing the denominator, the trick to this kind of a problem, and it's not an obvious, well, of course you do that. That's why I'm telling you right now. Here's what you do on this type of problem. You rationalize instead the numerator. So, what do I have to multiply that numerator by to make that square root go away?
Square root 2 squared plus 9.
Minus 3.
No.
No, why not?
Square root of t squared plus 9
Minus 3.
plus 3.
I forgot.
Wait, technically can't that just come out though and become t plus 3 minus 3?
Only worms cancel terms, and only worms take square roots of terms. Can't take the square root of terms. It just doesn't work. This has a name. Anybody remember it? High five that boy and girl if you remember the name. Nice. It's a conjugate pair. Square root of t squared plus 9, square root of t squared plus 9 minus 3, square root of t squared plus 9 plus 3. That's a conjugate pair. And when you multiply those guys together up there, fun stuff happens. Now it's a binomial times a binomial. Fun word of the day is FOIL. And so first times first. When I take this one times this one, they just go away. Right? And you just get t squared plus 9. Look what happens when I do the outside one. That's positive 3 times the square root, and then the inside one, negative 3 times the square root, and they cancel out and go away. And then negative 3 times positive 3 is minus 9. Now notice this denominator, I didn't distribute it.
Yeah, that's a waste of time.
Because what the goal of this is to get to a place where I can substitute in 0, and this is the problem I'm having down there, that t squared. And so I don't want to put the t squared in because on these types of problems, they're set up for you. Well, what happens is that t squared is going to go away. What happens to the 9 in the numerator? And then look what I got. I got a t squared over t squared times, and now these guys cancel. Leaving behind now, you remember at the beginning of the year last year when we did limit of the difference quotient? And I yelled at you all the time. You have to write the limit as, in this case, t approaches 0 on every single line until the moment you take the limit. It's got to be there. I'll mark it wrong. Look both ways. So, once I get to this point, now plug in 0 into that problem. So, 0 plus 9, let's get 9, square root of 9, 3, and you get 1, 6. Questions, comments, thoughts? There's a lot of arithmetic on that. So here's what you're supposed to be able to get out of here. Given some kind of a function, be able to evaluate the limit. Often a limit can be found just by substituting a number in. But the more interesting problems, that can't happen. And you have to do some work. This was one example of that, where you had to rationalize the numerator. But often it's just factoring. Listen to the vocab I'm saying. Often it's just factoring. And you can cancel common factors. So simplify the expression, and often something will cancel out, like it did in this situation, and then you're going to be able to substitute in the value that you're interested in. The end.